Hello and welcome back to another video here on the School of Quantum. Today we're looking into a company called Qphox, and they say that they've been solving the problem of information transfer from room temperature down to your superconducting qubits. And if you want to learn more about this and how this might get a breakthrough in the scaling of quantum computing systems that require cryogenics, then stay tuned for today's video as we are diving into Qphox. One thing before we start with the video, the statistic shows that a lot of people that are seeing these videos, they have not subscribed to the channel. So if this is the second time that you are seeing a video or the third time and you like these videos, please make sure to subscribe. It helps the channel to grow and it helps us as a School of Quantum to get the message out there. But with that, let's start right into the video. So, as I said, one of the major issues in today's scaling when it comes to superconducting qubit systems is the transfer of, let's say, readout lines and signal lines into the cryostat. Why is that? Well, technically, the qubits, they are sitting at a very low temperature in the millikelvin regime, so minus 273 degrees Celsius below zero, so very, very cold temperatures, and actually very close to the absolute zero. And in order to achieve this, you need a very sophisticated cooling technology. Usually it requires helium dilution refrigeration. There are also other techniques we've talked about in previous videos. Go check out the Hidden Quantum Champions playlist if you want to see those. But coming back, so usually these techniques, they only allow to cool down a couple of microwatts of power dissipation, or generally they have a cooling power of in a microwatts regime. And on the upper stage, like on the room temperature stage, for the first cooling stage, you spend kilowatts of power to actually achieve this. That said, if you now scale your chip with the superconducting qubits, you basically also need to scale the number of control lines, so the number of lines that bring the signal down to the chip and that can also read out the signal from the chip. Doing so, you strip all of these lines and thereby you create temperature bridges. So because of the fact that these cables are electrically well conductive, there's also a relation that makes them conducting well, not only the electricity but also the heat. You might know that if you, for example, have ever touched a copper pipe, you can feel that when like hot liquid is running through them, they're very quick in warming up. And you might also know that from the kitchen because, let's say, in the very high class kitchen equipment, you will find that they have copper pans. Also, when you do chocolate stuff in the oven, not in the oven. If you do chocolate stuff in your kitchen, you also sometimes use copper pans, and the reason for that is that they are very, very good in moving the heat, and they are very good in conducting electricity. Now, if you're thinking about stainless steel, I mean, it's also used in the kitchen. It's conducting less the heat. It's also conducting a bit less the current. Hence, it creates more dissipation. So the dissipation, the heat dissipation is also a function of the resistance of your system. So that means when you build a line, a signal line in using stainless steel cables, then you will end up dissipating a lot of heat down in your system where the chip is sitting. So you have to have these interfaces with different types of cables on different stages, and you will always be transferring some heat down into your system. And you also need to make sure that there's like various filter stages so that like thermal high energy electrons, they don't make it down into the system because also they create noise in your signal. So ideally, for that reason, there are like different ideas of how to solve that. One is to use superconductive cabling down in the cryostat. That is something that is available. I've also talked about companies that are, let's say, offering those. There are other ideas of moving down the whole electronics into the cryostat. So basically building signal generation and also signal readout electronics based on superconductors that are running down in the cryostat. But still, you will always have this connection between, let's say, the outside, where your signal is finally being read out, and the inside, where you do all of your signal generation and the readout. And now, with all of that said, today's company, which is Qphox, they are offering a solution to that. Or they are, let's say, coming with a new idea of how to solve this. So the motto is delivering on quantum potential, the gateway to scalable quantum computing. So how do they do that? Let's go right into the technology, right? So explore new technologies and products. At Qphox, we are pioneering the future of quantum computing by bridging the gap between classical and quantum technologies. So that's the quantum chip and the signal generation, right? Our journey is driven by a commitment to solving the most complex challenges in quantum computing. And here you can already see the magic ingredients. So it says Qphox Optical Control System. And then you see the quantum transducer and the cryogenic microwave switch as components to the product offering. So how does it work? I think we can read a little bit about that here. So coherent conversion by optically accessing qubits. Our patented quantum transduction technology presents the first viable solution for scaling the performance of today's most advanced quantum computers through connectivity and parallelization. So most advanced is always a question of how you define that, right? So the ion people will say that they have the most advanced, the neutral atoms might say that they have the most advanced. Maybe the superconducting people will say something else. We are currently in a technological race. We see all of these different technologies. These are just 3 examples. There are even more technologies that are racing for, let's say, the best performance of quantum algorithms that can actually produce some beneficial outcome. So here the idea is, and that's kind of the major clue, right? They want to use optical connections. So similar to what we know works well for data centers today, where you have optical fiber connection between 2 data center sites. They want to introduce this into the quantum computing system. So basically, you create your signals on the outside, you pass them via a fiber in an optical way down to your cryostat, and in there you then transform them again into electrical signals where they can be applied to your quantum processing units. You probably need to have some power lines for these units that are still sitting, let's say, down at the cryogenic level, but 2 power lines is still much less heat that goes down there than, let's say, a whole bunch of signal lines which we have in current setup. So like hundreds of lines that go down to drive, tens of qubits. Now, how does that actually work? What is the, let's say, secret sauce here? So, designed for scaling, fabricated for performance, our single photon interfaces leverage decades of progress in photonics, MEMS, and superconducting nanofabrication. They bridge the gap between microwave optical and telecom frequencies and provide the essential unbroken quantum links between computation, state storage, and networking. So here we have the secret sauce, right? They are able to transform between telecom frequencies, which is what works well at room temperatures with these classical fibers, and then the microwave optical regime, which is what you actually need to drive the qubits. Usually you are in the gigahertz regime, so microwave frequencies, and they have found out a way to do that. And this is kind of what is sitting behind this. So maybe they don't even need a power supply. I'm not sure about that. But just transforming the optical signal into a microwave signal that can then be applied directly to the qubit and read out again. But I guess there will be some power supply also sitting down there. Long story short, though, so this is the, let's say, the major technological ingredient here, right? So the transformation between those, and then in room temperature you generate your optical signal, you pass it via a telecommunication fiber, which is very well in conducting light, but is very low in conducting heat because it's basically an insulator. A fiber is not electrically conductive, and hence it doesn't carry a lot of heat down into the system. So that's basically the idea. And then it says also here, the major benefit, right? Transfer information, not heat. Our transduction technology brings high capacity, low thermal conductivity, optical data lines to control, measure, and interconnect quantum systems at scale in the most extreme cryogenic environments. And then here we see this transducer. We will also look at the products a little later, and the microwave part, which I guess is here with these coaxial connections. And this looks like an optical fiber here. Maybe I'm wrong though, not sure about that because it also connects here to this BNC socket. But these might be optical fibers here. Okay, and then of course there's some call to action to meet the team. Then we see some news section down here. I'm recording this in April of 2026. So we see here mid of March 2026 of the latest news, which is Qphox's work package leader in the European quantum pilot line, Supreme. And there's many more here, like for example this one, 50 million European quantum pilot P4Q to start in 2026, and so on and so forth. We see some information about the investors here. I'm not going to go through all of this now, but in the investors we see, for example, the High-Tech Gründerfonds from Germany, but also the European Innovation Council. We see partners that we've talked about before, like the Quantum Internet Alliance, the QUIC Consortium, and IQM, Rigetti, Qphox, and so on and so forth. Supported by, and then many labels. And finally down here, the newsletter and the note that this company is based in Delft, which is one of the major European quantum hubs as of today. Now, let's quickly check out the products, because I think that is what we are all here for, right? We want to learn what do they actually sell and how does it contribute to the, I think we understand now how it contributes to the overall quantum technology stack. So our products explore our range of products designed to meet the rigorous demand of quantum systems, pushing the boundaries of what's possible in cryogenic and quantum technologies, explore new technologies. So the first one we've seen that before is the quantum transducer, which is taking the signal down to the cryogenic stage, I guess via an optical connection. It says the Qphox quantum transducer provides the first quantum interface between single optical and single microwave photons. As the missing link between microwave and telecom-based quantum systems, the Qphox quantum transducer brings large-scale networking to the most powerful quantum systems. Product features are ultra-low noise, ready for quantum applications, high rate, high bandwidth, and high efficiency, coherent maintains phase down to the signal photon level, minimal power dissipation inherently built to scale, then qubit compatible, works with all MW, so microwave based qubit systems, so not only superconductive but also think about things like spin qubits that are also operating based on microwave signals, and then fully integrated platform, minimized footprint, distance-ready native telecom C-band compatibility. And if you want to know about the C-band, make sure to check out the Hidden Quantum Champion series, where the playlist where I also talk about the telecom bands in a different video. I think it was with Toshiba Quantum Technologies. Then the next product we see is the Qphox optical control system. So that's the box that would sit at the room temperature, and this here is the connector basically to the low temperature, right? So the Qphox optical control system, transfer information, not heat, trademarked. The Qphox optical control system offers a full solution for delivering radio frequency signals to the most extreme cryogenic environments, reducing the need for coaxial cables and attenuators and serving the thermal connection between room temperature and the cryogenic environment. The Qphox optical control system maximizes the system size possible in any scale of cryostat. Product features are end-to-end arbitrary radio frequency pulse in, arbitrary radio frequency pulse out. So that's in the pulse generator for the people that use pulse generators, right? Then transfer information, not heat, ultra-low thermal conductivity, optical fibers bring the signal into the cryogenic environment. Would also be interesting, I think, if somebody from Qphox is watching, to have a comparison like this little bars where you show this is the usual heat transfer, like the heat conductivity of a normal cable, like a normal coaxial cable, and this is what an optical fiber has. Are we talking about half, or are we talking about one order of magnitude smaller? Something like this. I think it would help to visualize. Then minimize thermal load, so heat dissipation only during active use, ready for exploration now, built to scale. and then maintain coherence and fidelity compatible with high fidelity quantum system control and read out. So yeah, basically it says it serves the normal things that you would do with your radio frequency pulses today, but of course in this optical way, which is better in terms of heat dissipation. And also I think worth mentioning, right, the heat dissipation, the main source of heat dissipation is sending those photons across the line, because they have to be transformed down into some radio frequency signals or microwave, which means there is an energy loss, right? Because if you take a red photon, you transform it down into a microwave signal, into a microwave photon, that means your energy goes down. The frequency of the light is connected or linked directly via the Planck constant to the energy of the light photon or of the photon. So transforming it down means heat loss. So with every photon that you send, you're, let's say, creating a heat loss inside the system, or you are dissipating heat. But then the other side is, if you're not running it, so if the let's say fiber is just dark, there's no photons running through it, it also basically doesn't dissipate any heat, which is different from the classical, let's say, electrical lines, which are constantly dissipating heat because they have thermal connection between the outside and the inside. So you cannot kind of turn it off unless you break it apart, which you cannot do, or physically disconnected, which you also cannot do. So yeah, that's a major difference also of the operation between those. Then finally, the cryogenic microwave switch control module. So our cryogenic switch controller has been tested and verified with Radial's cryogenic switch modules, and then we have a couple of numbers here, and should also be suitable for most other cryogenic modules of the Radial Ramses series. For more information on the switches, please inquire directly with Radial. Product features designed for use with Radial cryogenic microwave switch, which is, I think, one of the, let's say, most common cryogenic microwave switches in the field. Then dedicated timing control logic on each channel, adjustable output voltage and pulse width, inductive load protected outputs, and then optimized pulse control and signal conditioning enables minimum power dissipation in cryogenic environment. Typical transient heating is less than a millikelvin per actuation. USB or Ethernet controlled, USB powered, and then control up to 4 separate SP6T switches from a single module. And these SP6T switches are the switches that were talked about up here, the microwave switches. So yeah, that's basically the product range, right? So you start with this, you have the microwave switch, you have the transducer, and you have the optical control system. As always, let's quickly check out also the company and the team a little bit. Besides that, there's some resources here with blog articles and scientific publications. So if you're interested more in the technology, go check this one out. What is very remarkable, I mean, it's quite a big team already. This is not just like 2 PhD students sitting in the lab and building stuff. And it's actually quite a diverse team. So we see that there's like 41% of women in this team, 37 people and 21 nationalities. So you have a very broad spectrum of inputs here with various different backgrounds. And there's also this nice image line here, picture line with all the different people that are part of the team, which I guess every once in a while needs an update. And yeah, there's also the call to action to become part of the team and apply here. With that said, I think we're already at the end of today's video. I hope you liked it. If so, and if you stayed all the way to the end, please make sure to give it a thumbs up. If you're interested in more videos, again, make sure to subscribe to this channel. I hope I could convince you that it's worth it until this point in the video. And if you have any other company which you want me to check out, then let me know down in the comments below. With that, I'm closing off today's video. I'm looking forward to see you in the next one. Until then, bye-bye.